Hi friends, so today I'm going to start lecture 2 on the aerodynamics course. I'm Dr. Ranjan Ganguly. Now today we are going to discuss viscous flow and introduce the concepts such as boundary layer, which is very important in fluid mechanics in general. So essentially viscous flow means that there is friction present in the flow. And as we know that in most practical problems, the effect of friction is very important, and therefore we need to consider viscous flow. Now, before the concept of viscous flow came up, there was a phenomena in physics known as the DAlemberts paradox. And essentially, if you contemplate flow taking place around a cylinder, then what people thought is that flow would take somewhat like this. So these lines here are the streamlines. And the effect would be that the pressure distribution on the forward surface would balance the pressure distribution on the rear surface. And according to this picture which you see here, what would happen is that there would be no drag created by the flow because the pressure on the forward and backward surfaces are essentially the same. So essentially this is of course not true. When you put a cylinder in real flow, you would get a drag. So this was the paradox, that why is the drag coming? Because according to this kind of theory of frictionless flow, there should be no drag. So what happens in a real flow is that there is something known as separation. And if you ever do an experiment in a wind tunnel, you will certainly see that the flow goes somewhat like this. The streamlines move on top of the cylinder and then they go in this manner here. And there is a small region here where the flow actually can have a reversal. So this is the phenomena of flow separation, and flow separation at the rear of the cylinder leads to pressure on the rear surface being less than that on the forward surface, and this essentially leads to the drag being present. Now whenever you put any real object in flow, you are going to experience a drag or a backward force which is going to act here. So that's a phenomena we see in real life, and therefore this drag phenomena comes about because there is flow separation and because there is friction and viscous flow present. So one of the ways to think about viscous flow is to look at the concept of boundary layer, and this concept is very important as far as the flow around any airfoil section is concerned. So we are going to take a detailed look at the boundary layer. Now if we go back to our frictionless flow theory, if we place an airfoil section in air, then what would happen is the streamline would just slip on top of the surface. So essentially the streamline would come here, there would be a velocity v1, it would go on top of the surface at another point, say point 2, there is the velocity v2, and then it would just go on here. Now if this was true, then if we presume incompressible flow, then I should be able to use Bernoulli's equation between points 1 and 2. So that should be certainly possible if we have frictionless flow situation. But actually what happens is somewhat different. Very near the surface there is a complexity in the flow which takes place. So let us look at that in detail. So what would happen is that the flow at the surface would essentially adhere to the surface because of friction between the air and the solid. So if we think about it, at the surface the flow velocity is going to be zero. So essentially at this point A here, the velocity is going to be zero. But as we go sufficiently far away to the point B, the velocity is going to match the velocity v2 here. So this essentially thin layer is known as the boundary layer, and within this boundary layer the flow velocity is changing from 0 to that value v2, which is essentially what we were using if we contemplated frictionless flow. So again, to recapitulate these important concepts, at the surface flow velocity is 0. In a thin region near the surface, the flow is retarded relative to the free stream. So essentially it's slowed down compared to the free stream. And the region here between A and B, it's called the boundary layer. Now generally we use this symbol delta to say how thick the boundary layer is. And also in this picture I have shown the boundary layer to be very thick here. This is just for illustration purposes. Actually, it is extremely small. Okay, so keep that in mind. Now we see here that the flow properties at the outer edge of the boundary layer can be calculated from a frictional flow analysis. So this is the very important concept in fluid mechanics, is that we can split the flow field into two regions. One region where friction is important, and this is the boundary layer. So if we remain inside the boundary layer, friction is important. However, if we get out of the boundary layer, then we have frictionless flow. So essentially what we have done is we have conceptually split the aerodynamics problem into two parts. The part which is inside the boundary layer, that is the viscous frictional region, and the part which is outside the boundary layer, which is the frictionless region. Now this very important concept in fluid mechanics was introduced by Ludwig Prandtl, a German scientist. So now this boundary layer concept has been proved experimentally and theoretically, and what has been shown is that the pressure throughout the boundary layer is essentially constant. So if we look at the point A and the point B, the pressure through the boundary layer is constant across this whole region. So this is something which is very interesting. So pressure distributions calculated from frictionless flow give accurate results at the outer edges of the boundary layer. So essentially we can use some of the equations we derived in the previous lecture if we are looking at the flow velocity at the outer edges of the boundary layer, that is at this point where this V2 is there on the surface of this boundary layer here. Now the statements I made before are reasonable for slender bodies such as airfoil and do not hold for regions of separated flow such as blunt bodies such as the cylinders I showed before. Now boundary layer thickness in general will grow as the flow moves on top of the body, and because of the presence of this friction we have something known as a shear force. So we use the symbol tau to represent the shear force, and at the surface we put tau subscript w, which is the shear force at the wall. So shear force has the dimensions force divided by area. So it's the typical dimension of a stress or of a pressure, and it is tangential to the surface and leads to skin friction drag. So this is an important concept to remember, that friction leads to shear force leads to skin friction drag. So that's why we need to account for friction if we are ever going to calculate the skin friction drag. Now, the flow can also be classified into two types, laminar and turbulent flow. In laminar flow, the streamlines are smooth and regular, and the fluid moves smoothly on top of the streamline or along the streamline. Now, in turbulent flow, the streamlines essentially can break up and the fluid moves in a random or irregular manner. So, again, the topic of turbulent flow is extremely complicated and researchers continue to work on it. It's a very mathematically onerous problem, and there is a lot of research which remains to be done on turbulent flow. So, let's look at both these types of flow and which is preferable for us, that we'll discuss later. So, essentially, these two type of flows are different in terms of the profiles they have for the boundary layer. So this is the diagram showing velocity versus the distance y of the boundary layer or the thickness of the boundary layer. So in a laminar boundary layer, the thickness is delta laminar. In a turbulent boundary layer, the thickness is delta turbulent. So as you can see, the typical laminar boundary layer is thinner compared to the turbulent boundary layer. If we see the velocity profile also, we see the turbulent boundary layer, the velocity goes somewhat like this, and in the laminar boundary layer it is given by the red line here. So remember that at the end of the boundary layer, the velocities are going to reach the same value, which is the free stream velocity, or in the case we were considering the velocity v2 here. Now if we look at this graph, we are going to clearly see that dv by dy for laminar flow at y is 0, that is at this location here, this slope is less than the slope for turbulent flow. So dv by dy, you can see here, is going to be a larger number. Okay, so this is a very important fact which we have seen today, and this can be observed from all kind of experiments and theory and so on. So this is going to prove that the tau of laminar is less than the tau of turbulent, and I will introduce tau in the next slide, so just hang on for some time. So the basic point is going to be that the skin friction drag is less for laminar flow than turbulent flow, and this is a very important concept which affects the design of airfoil and wing sections on a lot of the airplanes you see around. So essentially in many airplanes, if you are trying to reduce skin friction drag, you can try to keep the flow as linear as laminar as possible. So that's something which people try to do. So now the shear stress definition at the wall is given by tau w is mu dv by dy at y is 0. So remember, the slope is always measured at y is 0, which is at the boundary layer surface. And this constant factor mu is known as the absolute viscosity constant, which for air is given by 1.7894 into 10 to the power of minus 5 kg per meter second. So this is a physical constant similar to density of air and so on. Now we can clearly see that tau is directly proportional to dv by dy, and that's why we can say that the skin friction drag in laminar flow is less than that in turbulent flow. Now viscosity typically increases as temperature increases. So if we go back to the boundary layer and look at it, the surface of the boundary layer is here, the outer edge of the boundary layer is here, and the velocity profile is somewhat like this. So at the outer edge of the boundary layer, Vb is equal to V2, and of course at the wall the velocity is simply 0, and this graph here, or this slope here, is going to determine for us what is the skin friction, because all the skin friction action takes place at y is equal to 0. So this particular profile here is very important. That means the dv by dy at y is equal to 0 is a very important number, because this is going to give us how the shear stress is going to be at the wall, and therefore if we can design the airfoil section to control this parameter, we can get different levels of shear stresses from the particular airfoil section we have. So that was today's lecture, where I essentially introduced to you the concept of viscous flow and the very important concept of boundary layer, and how the fact that the boundary layer is essentially the way we can figure out what is skin friction drag, what is shear stress, and so on, and also the very important concepts of the laminar and turbulent boundary layer. So in the next lecture, I'm going to discuss about Reynolds number and some effects involving flow separation and so on. So I will see you in the video sometime soon. See you then.